everybody, and welcome to our second unit on gas laws. And our first one that we are going to talk about in this unit is what's known as Avogadros Principle. And Avogadros Principle tells us that if you have equal temperatures and equal pressures, equal volumes of gases will contain the same number of molecules. So in the last unit, our number of molecules stayed constant. Now we're going to bring in amount of substance into the discussion. So again, if you're at the same temperature and pressure and you have the same volume, that means you have the same number of molecules, regardless of the type of gas you're dealing with. This is also known as the molar volume of a gas. All right, at STP, and remember STP is standard temperature and pressure. All right, 1 mole of any gas has a volume of 22.4 decimeters cubed. And remember, a decimeter cubed is the same thing as a liter. Okay, so again, 1 mole of any gas at STP has a volume of 22.4 decimeters cubed. All right, so now it's time to put all of our variables together: pressure, volume, temperature, number of particles, all into one equation. And we call this the ideal gas equation. So this should get a big star highlight in your notes. All right, ideal gas equation. And we write the ideal gas equation like this: PV is equal to nRT. Now, P is pressure, V is volume, T is temperature, N stands for our number of moles. Okay, so our moles. All right. R is a constant, and it is a value that allows you to relate all of these other variables. Okay. We can calculate R by using STP and the molar volume of a gas. So what do I mean by that? Well, I'm going to take this equation and we're going to solve for R. And when you do that, you get that R is equal to pressure over volume, pressure times volume over the number of moles times the temperature. So now let's fill this in. We said standard pressure. We're going to use R in terms of kilopascals. All right, so that means you have 101.3 kilopascals as standard. Our volume, remember, is 22.4 decimeters cubed. Number of moles is 1 mole, because all we're using is this idea of molar volume of a gas. And the temperature is standard temperature, so 273 Kelvin. When you do this calculation, you are going to get a value of 8.31. All right, and then the label, if you notice, is kilopascals times decimeters cubed over moles times Kelvin. All right, so you do need to make sure you have this value handy. All right, divided by moles times Kelvin. Because this value for R, we're going to use quite a bit in this unit. And you have to remember, anytime you use 8.31, this R value, your other units with it must be in kilopascals, decimeters cubed, moles, and Kelvin. So as we move on, please remember that we will be using this value quite a bit. All right, so let's just do a little bit of practice using the ideal gas equation. All right, number 1, what pressure is exerted by 4.5 moles of gas in a 198 liter container at 8 degrees Celsius? So remember, we're dealing with PV is equal to nRT. Sometimes people call this pervnert. It's just kind of a funny little saying that we sometimes use. But again, your ideal gas equation, we're looking for pressure. I like to do my algebra first. So that's going to be nRT at the top over V. N is your number of moles, so 4.5 moles. All right, abbreviation for moles is mole, just without the E on it. All right, then R is 8.31. Your temperature, remember, has to be in Kelvin, so the temperature is 8 degrees Celsius. 8 plus 273 is going to give us 281 Kelvin. And then your volume is 198 liters. Remember, a liter is the same thing as a decimeter cubed, so I can leave it in liters. All right, so there we go. When you punch that into your calculator, you get about 53.1 kilopascals. Okay, and again, if you're wondering, how did I get kilopascals? Well, if I write out all of my units of R, all right, the kilopascals will be the only one that divides out, because remember, the units are kilopascals times decimeter cubed over moles times Kelvin. Okay, so let's look at number 2, because number 2 has an extra step in there. What mass of oxygen gas will occupy 450 milliliter flask at 11 degrees Celsius and 66.7 kilopascals? Well, I'm looking for mass. Okay, our ideal gas equation does not have anything directly dealing with mass, but we know from all of our months in chemistry that if I have moles, I can very easily convert to grams, all right, which is our mass. So in this problem, I'm going to solve for N. Okay, again, I like to do my algebra first. PV over RT. Okay, my pressure is 66.7 kilopascals. My volume is 450 milliliters. Remember, that needs to be in liters or decimeters cubed. So we're going to go on ahead and convert that. That is 0.45, all right, liters. R is 8.31. And our temperature is 11 degrees Celsius. 11 plus 273 gives us 284 Kelvin. When we solve for this, all right, we get about 0.0127 moles, okay? All right, now that was not what I asked for. I asked for mass. So now it's time to take that 0.0127 moles of oxygen gas, which please remember is O2. You do need to remember your diatomics. Okay, 1 mole of O2. We're going to look at our periodic table. A single oxygen atom is 16, so O2 is 32 grams. And when we multiply this out, you get about 0.41 grams as your final answer. So here were just 2 examples of how we use the ideal gas equation in some pretty straightforward examples. All right, so now let's look at another way that we can use the ideal gas equation, and that's to determine molecular, otherwise known as molar mass. So also known as molar mass. All right. When we talk about the number of moles of a substance, it's equal to a mass, a sample mass, divided by the molar mass. This is actually something we've done tons of times throughout our months. So what we do is we say, here's my ideal gas equation. So I have PV is equal to nRT. All right. Well, if I think about what moles means, as I said, moles is a mass, a sample mass, okay, divided by the molar mass. And the sample mass is going to have a unit of grams. Molar mass is grams per mole, and we're going to abbreviate that with a capital M. All right, so what does that mean? So this instead, it becomes PV is equal to little m, all right, and little m is your mass in grams. It's going to be the sample mass, all right, times RT over molar mass. So this is how we play around with the ideal gas equation to involve a specific mass and the molar mass. I'm going to then rewrite this to give us this equation. Capital M, which is molar mass, is equal to the sample mass times RT over PV. This is one you want to star because this is what you're going to be using in these calculations. We'll also do a lab that's very similar to this. So again, capital M, which is molar mass, is equal to your sample mass, that little m is sample, times RT over PV. So let's take a look at an example. What is the molecular mass, otherwise known as molar mass, of a gas if 150 mils has a mass of 0.922 grams at 99 degrees Celsius and 107 kilopascals? All right, well, here we go. We're looking for capital M. My sample mass is 0.922 grams. All right, R is 8.31. And we remember the units for R, kPa, and you don't have to write these every time, times decimeter cubed over moles times Kelvin. All right, then we are looking for our temperature, 99 degrees Celsius plus 273 is 372 Kelvin. over our pressure, which is 107 kPa. All right, times our volume, and our volume is 150 milliliters. So please remember that is 0.15 liters or decimeters cubed. They mean the same thing. All right, and as we can see, kilopascals divide out, Kelvin divides out, decimeters cubed divide out. All right, what we are left with is grams divided by moles. That is the definition of molar mass. All right, we're gonna go on ahead and put this into our calculator. And when you do, you get about 177.6 grams per mole. Remember, molar mass has to be a value over 1, so always kind of check that as you go. All right, final thing we're gonna talk about today is manipulating the equation one more time. All right, so we can talk in terms of density. So we can also use, all right, our equation to solve for density. Remember, density, all right, is mass divided by volume. All right, if we take our equation here, okay, and manipulate it algebraically to get mass over volume, what you're gonna have is this. D is equal to M over V, that's what density is. M over V is gonna be pressure times molar mass over R times T. All right, so this is gonna be the equation that we're gonna use when we're dealing with density. So let's take a look at the example. What is the density of a gas with a molar mass of 44 grams per mole that has a pressure of 150 and a temperature of 200? All right, great. Well, we know mass over volume is density, and that's going to be PM over RT. Okay, our pressure, 150 kilopascals. Our molar mass, 44 grams per mole. R is 8.31, and our temperature is 200 plus 273, so that gives us 473 Kelvin. All right, we punch that in our calculators and we get our density is equal to 1.68 grams per decimeter cubed, or liters, however you would like to write it. All right. Okay, we're gonna do a lot of practice and some labs with our ideal gas equation. So have a great day.